So these were the lightweight standards. Let's say some final words about block ciphers. As we talk about Feistel and SPN, and you might ask which one is better. Actually, there is no answer to this question. Again, it is a matter of taste, and it also depends on the application. You might choose one of them for better implementation, let's say. The pros maybe can be simply said as follows. Encryption algorithm in the Feistel networks is identical to the decryption algorithm. Only the order of the round keys change. So this means that you don't need the inverse operations of round functions for decryption. So this would actually help you to implement the cipher on hardware because they would require less gates. But the good thing of the substitution permutation networks is that a single round affects the whole input. As you recall, at the Feistel, we divided into two halves. Only one half is affected from the round operation. So both of them, actually inverses of these sentences can be provided as cons. In Feistel ciphers, a single round only affects half of the input. And for the SPN, the decryption procedure requires the inverses of the substitution and permutation layers. But of course, this is the case if you are using a simple mode of operation, let's say. Our next topic will be mode of operations, and sometimes, depending on your choice of mode of operation, you actually might convert your block cipher into a stream cipher, which means that the encryption and the decryption actually performs the same operations. So this sentence does not valid when your mode of operation is something like counter mode. So you don't have to implement the decryption algorithms in the hardware if your mode of operation is something that doesn't require the decryption operations. Okay. So what are the design considerations for different platforms? Hardware versus software is as follows. Hardware implementations can easily work on bits. Since most programming languages focus on bytes, bit operations are more costly on software. Cipher design also determines the number of gates required to perform encryption on hardware. Number of gates determine the area required, which also affects the cost of manufacturing the device. Code size or required memory is not a big problem for software implementations due to fast CPUs and large memory. But of course, in this course, we are not focusing directly to the desktop computers. We are looking at small devices. And let's look at security versus speed. Speed is generally measured as throughput. We are actually looking at the megabits or gigabits per second. Adding more security measures, for instance, increasing the number of runs, increases security but reduces the speed because you're adding more operations. But maybe we should mention something. This increasing the number does not always provide better security because there are some attacks, depending on the weakness of the cipher, that would be valid for any number of runs. Like if invariant subspace attack, if there is an invariant subspace in the cipher, then it would be valid for any number of runs. Ciphers performing well on hardware or software may not be suitable for constrained devices like RFID systems or sensor networks due to limited memory, battery, or computational power. And this is what we were talking all the previous weeks. This is the main reason we need lightweight ciphers in the first place. And probably we haven't talked before, but I said that short keys are not good and lightweight crypto is not about short keys. So an attacker that captures a single ciphertext can try to decrypt it with every possible key to check if it provides a meaningful plaintext. Such an attack is called exhaustive search or brute force attack. So you are trying every possible key in the key space. Exhaustive search is a generic attack. In other words, it is valid for the cipher, for every cipher, and it doesn't concern anything about the design of the cipher. It is just a brute force attack. For a k-bit keyed cipher, the attacker is required to perform a most 2 to the k decryptions or encryptions, because we are assuming that you capture a single ciphertext block, but if you know also the plain text block that corresponds to the ciphertext block, then your exhaustive search turns into 2 to the k encryptions. You perform this encryption and check if the ciphertext block you observe is the same with the one you captured initially. Thus, security of a block cipher is upper bounded by exhaustive search. In other words, 2 to the k encryptions or decryptions again. If one of them is faster than the other, then you may use the other one. This quantity is referred to as time complexity. So how hard is the exhaustive search? So if you look at the key size of this, which was 56 bits, all you need to is to perform 2 to the 56 encryptions of this, which is this many encryptions. But I can say that a GPU can perform 2 to the 32 DES encryptions in a second. So using a single GPU, you can break it in less than a year, in a few months. But if you have a few hundred GPUs, you can break it in a few days. And a lot of people gather on the internet, and instead of using video games, if they use their GPUs to break this, they can do it in a few seconds. So this number is really small. For present, we need this many encryption operations, but as you can see, this number increases exponentially. And for AES or any other block cipher that uses 128 bits, the exhaustive search becomes really hard, because, for instance, assume that somebody has enough computational power to perform 2 to the 80 encryptions in a second. So assume that somebody can break present in a second. So a year has around 2 to the 27 seconds. So somebody who has this much computational power can perform 2 to the 107 encryption operations in a year. So they need 2 to the 21 years to break a cipher with this length, which has key of this length. So they need more than 4 million years to break it. So even if somebody has the computational power to break this in a second, our keys of length 128 bits would still be secure. Of course, the technological improvements convinces us that we are secure with this key length, but for military use, you can choose to have longer keys so that you protect your data for hundreds or maybe thousands of years. Of course, this only might change if there's a different technological advancement, like if somebody can build a general purpose quantum computer, then the security of these numbers actually becomes their square root. So at 256 bits, secret key would provide actually 128-bit security, which would still be secure even if somebody builds a general purpose quantum computer. But we don't have quantum computers today for this purpose, but we have CPUs, GPUs, FPGAs, or ASICs. So GPUs have a lot of cores, so in parallel processes, they are better than CPUs. Generally, a GPU has now more than 3,000 cores, but a CPU core is better than a GPU core. They have a lot of more functionality. We have few programmable gate arrays, which can perform, again, general computing operations. But if you burn into a silicon and obtain a dedicated device, then we call them ASICs, which provide better performance with respect to the cost. This is why Bitcoin miners or some other cryptocurrencies are using ASICs for mining. So a question might arise as follows: how many rounds a cipher should have? There is no direct answer. The common belief is that increasing the number of rounds increases security. However, it will decrease the performance. A common practice is as follows: designers apply every known cryptanalysis techniques, and if they can break n rounds, then they choose the round number R as bigger than or equal to twice the number of rounds they could break to stay on the safe side, because attacks always get better. People find people find more weaknesses, or people get or invent new cryptanalysis techniques. So designers try to stay on the safe side. So even if they can attack more than n rounds, they will still be not enough to break the R rounds. And these are some standardized block ciphers. For NIST, there are only two standards now, AES and triple DES, which is using DES 3 times. Skipjack can be used for legacy use because it only supports 80-bit key, which is not considered secure by NIST. But ISO has more standards, and Cryptography and Present are standards for lightweight crypto. HIDE is also a lightweight standard, but it is theoretically broken, so there's no point of using it when we have other algorithms. So some problems arise when we are using block ciphers. The first one is key management. Keys must be exchanged between the communicating parties before they can use the block cipher. To communicate with M people, one has to securely exchange N keys. Some solutions are using public key encryption algorithms, but they are slower than block ciphers. Or you can use key exchange algorithms like Diffie-Hellman key exchange, which comes from public key cryptography. But if we are focusing on the Internet of Things, so we have very limited capability of devices, so they cannot perform these kind of public key algorithms. I mean, not all of them can perform these operations. So when designing a network, we have to think how we update the keys, because we don't want to use the same key for the rest of our lives. So this is one thing we have to focus. Also, another thing is key storage. Storing keys directly on the hard drive or RAM can be a problem, but also this sentence for actually personal computers, but again, in our setting for the IoT, storing keys, we have to store it somewhere, and if we store it in the device, we have to be sure that if somebody stole the key, stole the device, we need to be sure that they cannot take the key out of the device. So we have to build these devices somewhat as tamper-proof. Another thing is the message length hiding. Plain text and corresponding ciphertext lengths are identical. We haven't talked about mode of operations yet, but if you encrypt a 1 megabyte of data, the result of the ciphertext is also 1 megabyte. The size does not change. If adversary knows the context of the communication, then they can guess the plain text just by the ciphertext length. So in our IoT setting, we have to be sure what we are doing here, because if we are sending, in some cases, only small sized plain text, and in a different case, if you are sending longer text, just by looking at the ciphertext size, the adversary can guess what the data we are sending. So this is something we need to also pay attention when we are designing our IoT network. Key generation is also a problem. To obtain k-bit security, the k-bit key should be generated randomly. So we need to be using cryptographically secure random number generators, or we can use password-based key derivation algorithms, but of course we need to choose a good password in this case.